now I'm going to give you an example of using the chain rule in a multivariable setting. So let's say you've got a surface looking like this, and x and y are governed by a variable t. So let's imagine t as being time, ticking along like this, moving along in this direction. So our job is to find the gradient with respect to time at time equals pi over 2. So let me just quickly paint the scenario for you. So here you've got a function looking like this. You input a time, so as time ticks away, it's going to tell you where the particle is in the x direction and in the y direction. And then our job is to find the change in w with respect to time. So this is what's happening. As time ticks away, so for a given time, the particle will move around like this. The particle will move around like this. It will move around in a circle like this. So this has a radius of 1, 1, -1, and -1. So the particle starts here, and then this is telling us the movement of the particle. So looking at the domain, looking at the xy plane domain, it's going to move like this in a circle. Well, in circles, it's going to move around like this in circles. But what that means in 3D, what it means is this. Imagine this is +1, this is -1, this is +1, and this is -1, and the origin's right here. So x axis is here, the y axis, hang on, bear with me, the y axis is in this direction here. So as the particle moves around like this, in 3D it will move around like this. Hang on. In 3D it will move around like this. It starts here when time equals 0, and then it will go uphill. So it will go uphill like this, and then downhill again, and then it's going to go downhill. So it's going to go downhill, and then it's going to go uphill, and then downhill, and then it's going to go downhill, and then it's going to go uphill in 3D. So it's going to look something like this. So on the plane it will just move around in circles like this. But in 3D it will go uphill, down, down, and then up, and then up, and then down, and then down, and then up, and so on. It's going to move around like this in 3D. But on a 2D plane it's just going to move like this. So our job is to find dw by dt. So looking at this, let's compute it now. So looking at this, using the chain rule, if we want to compute this, we got to find the partial derivative of w with respect to x, and then multiply it by dx by dt. Well, okay, let's compute this first. So looking at this, differentiating it with respect to x, meaning y is a constant. So when you differentiate it with respect to x, it's just going to give you y. It's just going to give you y. And then now we've got it times by dx by dt. So looking at this, dx by dt is you differentiating this. So that would be minus sine t. So that will then give you this, and then you've got your plus. So now we'll work out the partial derivative with respect to y. So looking at this, we're differentiating it with respect to y. So x is a constant. So when you differentiate it, it will just give you x. So this thing here is just x. And now looking at the y, dy by dt is cos t. So this thing here will become cos t. So now it's just a matter of tidy this up. That will then give you this. So now what is x? Well, x is governed by this. So we can put this into here. So and then we can put this into the y. That will then become cos squared and cos squared minus sine squared. So that will then take us to here. But then we want to know the derivative with respect to time at time equals pi over 2. So so if you put this into here, remember cos looks like this. This is 2 pi. This is pi. So pi over 2 is 0. So this thing here would be 0. 0 squared is going to be 0. So that's going to be 0. So this thing here is going to be 0. And then you've got your minus, and well, put this into here, it will give you 1. So you're going to have negative 1. Okay? So at this stage, at this stage, I'm just asking you to blindly compute dw by dt. We don't know what it means yet, but over time I will give you an example. I will give you more examples, and then over time, hopefully, you will understand the meaning of dw by dt. At the moment, we are just merely computing dw by dt. Over time, I will give you more examples, and then hopefully in the future you will understand what it means by dw by dt. Okay? At the moment, we're just blindly computing this thing. Okay?